Hello everyone, we're going to begin our study of related rates, so hopefully you have something that you can write down. So suppose you have a circle that's growing as time passes by. So it starts off with this area, and then it gets a little bigger, and then it gets a little bigger, and then it gets a little bigger and a little bit bigger still. So it's growing as time goes along. Now if both the radius r and the area A are changing with time, that means the radius r and the area A are functions of time, which means we can write it like this, area as a function of time. So a typical related rates question is, how are dA dt and dr dt related? And the follow-up would be, when the radius is 5 and it's increasing at this rate of 2 centimeters per second, how fast is the area changing? In order to answer these questions, we're going to have to start off by taking the derivative. So the derivative of A would be dA dt. Pi is a constant, so it comes along for the ride. The derivative of r squared would be 2r, and then dr dt. Now sometimes the t's, the function notation, it confuses people. So without the t's, this is what it would look like. Again, the derivative of A is dA dt. Pi is simply pi, and r squared is 2r times dr dt. Now we can plug in what we know. When the radius is 5, that means we can replace the r with 5. And we know that the radius is increasing at a rate of 2 centimeters per second, which means we can replace the dr dt with 2 centimeters per second. Multiply all that together, and that tells us that dA dt is 20 pi square centimeters per second. That is the rate of change of the area of that circle. I had another question. Suppose we have a spherical water balloon, and it's releasing water at a rate of 1,000 cubic centimeters per minute. When the balloon's radius is 10, how fast is it changing? To do this, we need to start off with our volume equation for a sphere. So the volume of a sphere is 4/3 pi r cubed. And we're going to take the derivative. The derivative of v is dv dt times 4/3 pi is a constant, so it just comes along. The derivative of r cubed is 3r squared times dr dt. From here, we can plug in the equation, the numbers that we know. So we know that the water is being released from the spherical balloon at a rate of 1,000 cubic centimeters per minute. Once we solve for dr dt, I can replace the dv dt with negative 1,000. And the reason it's negative is because it's being released. It's getting smaller. The rate is getting smaller. When the balloon's radius is 10, then how fast is it changing? We can replace the r with 10, do a little bit of work on this, plug it all out, simplify it, and you can see that there's your answer, negative 5/2 pi. The negative sign tells us that the radius is decreasing. Alright, so here's another problem. One end of a 5-meter ladder is sliding down a wall at a rate of 1 meter per second. At what rate is the angle of the ladder with the floor changing when the other end is 3 meters from the wall? So we draw a picture, we have everything labeled. We're interested in the angle of the ladder. How fast is the angle changing? So we need an equation that relates these three different sides in this angle to each other. And what we're looking for then is we're talking about a sine of theta. So the sine of theta is the opposite over the hypotenuse. So the sine of theta is h/5. We want to know how fast is the angle changing. So we want to know d theta dt. So we need to take the derivative. So if we start off with h/5 equals sine of theta, and we take the derivative, well, h/5 is 1/5. So that's a constant, so it comes along for the ride. So we get 1/5 dh dt. The derivative of sine theta would be cosine theta. The derivative of theta would be d theta dt. We're always going to use radian measure when we're doing anything with trig functions in here. We know that one end of the ladder is sliding down at a rate of 1 meter per second. So since it's going downward, it's a negative 1, and that's the side of the ladder. So that's dh dt. Then, if I plug that in and if I solve for d theta dt, I'm trying to get the d theta dt by itself. So I divide it by the cosine of theta. I need to plug or replace that cosine of theta with something. Looking at this picture, remembering your trig rules, the cosine of theta is adjacent over hypotenuse. So the cosine of theta is 3/5 in this case. Therefore, I can replace the cosine of theta with 3/5. And if I multiply that bottom out, I wind up getting negative 1/3, and this is in radians per second, is the angle at which, the rate at which the angle of the ladder is changing. Okay, water is draining from a cylindrical tank at 3 liters per second. How fast is the surface dropping? Well, first of all, we know dV dt. That is the rate of change of the volume. So the volume is draining it out at negative 3 liters per second. I'm going to convert that into centimeters cubed, so negative 3,000. Next up, we need to find dH dt. We're trying to find how fast is the surface dropping. We need an equation for the volume of a cylinder, and that equation we're going to use is volume equals pi r squared h. Now, we're going to take the derivative of that, and we're going to get dV dt equals pi r squared dH dt. Now, one trick for this problem is to remember that for a cylinder, r is constant. The radius is the same all the way up and down that cylinder. So since r is a constant, the pi r squared just comes along for the ride. We don't do anything to it. The derivative of h is dH dt. Now we can plug in what we know. We know that dV dt is negative 3,000, and we're looking for dH dt. So we can then divide, and we get dH dt is negative 3,000 divided by pi r squared. And that would be our solution to our problem. The steps for related rates problems, so you should write these down. Step number 1, you want to draw a picture, a sketch. Number 2, you want to write down what you know. Usually that means writing down and labeling the sketch and writing in the information that we know. Step number 3, we want to write down what you're looking for. Right? It's very important to write down what it is you're actually looking for, so that way you can keep that in mind as you're solving the problem. Step 4, we want to find the equation and write it out that relates the variables together. So we're going to be doing lots of different types of equations in this chapter, so we want to make sure we identify which equation do we want to use for which problem. Next up, we're going to differentiate, take the derivative of both sides, and lastly, we're going to evaluate by plugging in the problem, plugging in the known quantities, and then solving for what we're looking for. Now, I know this was a very fast intro, and we went through a couple of problems really quickly. We're going to do several more problems in class tomorrow and throughout the next week or so as we're going through this unit. So hopefully this helps get you an idea of the basics of what we're talking about and what we're going to be doing in this chapter, and I will see you in class tomorrow.